Hello guys, if anyone can give me a thumbs up for the sound, just to make sure that we're all good, that'd be appreciated. Thank you, Ian and Marco. We'll start here in about 4 minutes. Thank you for your patience. Yeah, Marco, sorry, the mic was muted. We're gonna start here right now. Let me just switch this to laptop. Okay. Okay, we can go ahead and, is the mic working, guys? No? You think? Okay, so let's go ahead and begin. We're at the class time mark. As usual, we'll discuss some details for the course, and then we will go ahead and start with our lecture, and that should be it. So Today we will be speaking mainly about, I know we spoke about DNS and we gave an idea of what DNS is, but today we're going to go more in detail about DNS and we're going to speak about like the details that get stored in the DNS. If you have a new host, how can they register themselves within the DNS? And then also part of the lecture today is we're going to speak about the content distribution network for video, and we'll have some examples of Netflix and YouTube. So before we begin in our lecture, so far where we in right now, we're currently in week 5. We had an HTTP and SMTP protocols that we discussed with Mobile Xterm and Eustace, and there's the 2 supports for these are there. The lecture is not being uploaded. That is because it's not being published. Okay, one moment. Okay, that should be published for you guys. And it's the same version that we have here. Okay, and homework 1 is going to be released very soon. I'll have an announcement when it'll get released. It's going to be something related to the application layer, obviously, chapter 1 or chapter 2 in the essence. And it's not going to be anything too major. We're going to just have questions related to the protocols that we discussed in class. So HTTP, SMTP, and DNS that we will talk about more today. Okay. Any questions on the Wireshark assignment on the class before we get started? Okay. We can go ahead and begin. In terms of the midterm, I believe it's gonna be in October, probably the 2nd or 3rd week of October. We're gonna have a week where you won't have a lecture for that week. Any of the lectures, it'll be just dedicated for your midterm. But as it's tentative, the date. As it gets set, I will make an announcement. And obviously in the upcoming lectures, I will announce and have a reminder of it. But as just we discussed, it's gonna be take home and you'll have like 48 to 24 hours depending on how lengthy it is. So that's for the midterm. Let's go ahead and share my screen. Okay, so part of the usual, the class is being recorded and ample of the portion of the material is derived from the book by J.F. Caros and K.W. Ross. So you can check that out on your own if you would prefer. So here's where we are in the application layer. We talked about the principles of the network applications in terms of application development. Then we dived into the protocols of HTTP. We talked about web HTTP. In the last lecture, or the last 2 specifically, we covered SMTP and IMAP with a little bit of hands-on. Also in the previous lecture, we talked about DNS, but that was just like the beginning of DNS. Today, we will go more in depth about DNS. We'll do some command line commands that are going to be useful with that go along with DNS. And today, we will also be able to talk about video streaming content distribution networks. So we'll have a review of the DNS. We'll review like the resolving queries, like iterative and recursive, and we'll look at DNS records and message formats. So let's go ahead and get started. So here is just a brief idea from a recap from the last lecture. We talked about DNS, and I just want to remind you of the iterated query that we have. We have a requesting host that is trying to get an IP address for the University of Massachusetts, and the host here that we have is engineering.nyu.edu. So what would happen is that we obviously want the IP address of this specific host, so we have to get it requested. So usually what would happen is that the requesting host would request to the local DNS server. And we said that the local DNS server is stored at every infrastructure and they're responsible of keeping it maintained and building it. So the local DNS server does not know does not know the authoritative or the IP address of the host because it does not have a copy of it. Because we said part of the local DNS is to keep a cache that it can remember the whatever that is getting requested, similar to web proxies and web caches. So the local DNS would redirect to the root DNS server, and we said when we speak from a hierarchical point of view, the root DNS server is at the top. After that, the root DNS server would not know, so it would respond saying, "Hey, I don't know it." It would go to the top level domain DNS servers. These are like the .com, .org, .edu. And here we have it .edu. So it'll say, "Hey, I don't have the address as well," but it will redirect it in the specific domain, the type of level of domain. So then it would request it from the authoritative, and the authoritative is basically the local for the host in essence. So they will have and they will contain information about their domain name systems and IPs. So it would send it back to the local. The local this time would keep a copy such that if we have another client within the organization and they do request it again, it would be stored and it would not have to be requested again or go through this process. So then it gets sent back to the requesting host. That is the aerated query. The recap of the recursive is a little bit different. And here we have the same idea. We want the host for University of Massachusetts.edu. We have a requesting host that wants an IP address. So the first thing gets repeated, it requested to the local DNS server. This is not a build-up on the last slide. So we are assuming that the local DNS still doesn't have the IP address. So the local would ask the root for help. Instead of it giving like a referral, the root server takes responsibility and queries the TLD server itself. It won't reply back to the local saying, "Hey, I don't have it." It would directly be responsible of contacting the TLD server. The TLD server as well will contact the authoritative. So recursive is just the idea of that the servers themselves handle the query rather than the local being the main asking point. So then the authoritative replies to the TLD, and the TLD goes back to the root, and the root goes back to the local, and then it gets sent back to the requesting. The local DNS would also keep a copy of that. And there's a difference with the recursive, as we said. Each server is along the chain does the work of contacting the next one. And in this recursive query, this puts more in a sense, more work for the upper level servers, especially the root and the TLD, since they carry the burden of resolution. Okay, so we talked about the two types, iterative and recursive. And we said that iterative queries put more burden on the local DNS. Recursive pushes the load on the higher hierarchy. Once a DNS server learns the mapping of the requesting of what is being requested, it caches that record. So caching reduces the repeated steps. As we said, the local would keep a copy of that, so we don't have to repeat the same hierarchy. And caches records stay only for a limited time. This is called time to live. When we apply hands-on today, and we'll try with a host, there will be a time to live such that the mapping will stay in as a record in the DNS server. So there's two benefits of caching. First one is it is faster response time for clients, and we said that it's similar to HTTP. We don't have to request the web page from the origin server such that we have it in the web proxy, it sends back. And it's less overall on the DNS infrastructure itself, from the top to the root to the authoritative. But it also has a limitation with the caching. Entries may become out of date, like if the IP of the IP address of the host changes before the TTL expires. This is why, like the DNS, when they describe it as best effort name to address translation. So updating the DNS records, it's update/notify. It's a mechanism that is proposed by the IETF. And the reference number for it, or the RFC, is 2136. That is to help with consistency and updating. We will see how that exactly happens. So now you might ask yourself, we said that the local DNS server stores info regarding, we want to know what does it store specifically? What does the local DNS server store? What kind of records? So each record has exactly 4 fields that we have to be aware of. And regardless of the request, those 4 fields remain the same for uh, each type of DNS record. So as you can see here on the top, we have the name, value, and type, and time to live. These are the 4 fields. And the name is basically the domain or the name system, the host name, like for the specific network. The value is the IP address. Sometimes we can have a canonical name or a mail server, depending on the type of the value. The type indicates the kind of record, and the time to live is how long the record is cached before expiring. So now, since we know that there's 4 fields that will be in every record type, let's look at the different record types that we have. We have type A, which is called also as known as A record, and maps the host name to the IP address. And this is the idea of the DNS in general, but each one of these records gives us various things. So example here that we have on the top, example.com, at means the root domain, and the value could be like, the value could be here, the IP address, time to live is 14,400 seconds. That is the time to live there. So that would be an example of the A address. The NS record gives us the authoritative name for the server, because we know that every server has an authoritative name. So domain like ucf.edu would point us to its authoritative server. And we will see that when we apply some various command lines. The CNAME is also, we said, an alias name for canonical, the real name. And we said that the host name can have an abbreviation for itself. So like Amazon can make theirs be AZ, just a shorter version that you can think of. The MX record maps a domain to a mail server that handles the email. So also the mail server also has a domain that we can keep or look into. So DNS ideally is a distributed database that has these specific records and mappings for web hosts, and has a load balance and email delivery. Now we have DNS protocol message, both the query that we request and the reply using the same format. Here we have each message starts with a header, and the identification is a 16-bit transaction ID that is used to match the replies with the correct delivery. We also have flags. It indicates if a message is a query or reply, whether it's recursion or requested, if it's available, or if the reply is authoritative. It determines what type of request is being happening. Now, following the header, the message includes various fields like question, answers, authority, and additional info. The number of questions is how many queries are being included. The number of RS is a count of resource records in the answer section. Authority would be the number of authoritative records, and there could be more than one. It doesn't have to be necessarily one. Additional RS also is the number of extra records, if there's extra records. Maybe you are kind of lost, but when we come to a little bit of the hands-on, it will be very self-explanatory. Also, the question contains the queries that are being asked. The answers contains the resolved. That's in terms of the reply. The questions would contain the answers to the queries that are being asked. The answers give the available resource records. Authority would give responses to the authoritative name servers, and the additional provides extra information like hints or faster resolution. So it's a query response protocol similar to HTTP, but the format is different here, and the fields are also different here. So In a query, the question section will hold the name and the type to be resolved. Could be like ucf.edu, asking for an IP address. In a reply, the answer would contain the resolved record for the query, and it would reply with an A record saying that, hey, this is the host name and its IP address, because we said the A record maps the IP address with the host name. And the authority section lists the authoritative servers for the domain. The additional section would provide like extra information, like maybe time that you requested, and if the query was successful or not. So as similar to every protocol that we have, the RFC defines all these fields and records, formats, and details, similar to SMTP, the email protocol. So now let's say maybe this could be you, if you have a company or you are starting something small and you need a DNS record. So here we have an example of a new startup, which is Network Utopia. Um, not sure what that name means, but that is the name. So to be reachable on the internet, the company obviously needs to register its domain name with the DNS registrar, which is here the network solutions. Think of it like the DMV. When you want to register your car, you have to go to the DMV for the registration to happen or to renew your license. So the register requires several things from the company. It requires the domain name and the IP address of the authoritative name servers, both the primary and secondary. And then the registrar would go and keep the information up to date in the TLD server. It would record, hey, this is a .com website or a .org or a .edu. And here we have an example. The host name is networkutopia.com. It would have DNS1 networking, networkutopia.com, and this is the NS type of a record. And it also has their IP address and the host name. So the next thing is that the authoritative name server here at the bottom that we have, it would respond locally. It would give it an IP address, a random IP address. We'll study that when we come more into the network layer. So it populates it with the sufficient DNS record. So an A record for Network Utopia maps the hostname to the IP. An MX record would specify the mail server. So registering a DNS or DNS register only provides pointers or like, hey, I need these specific requirements from you. And the actual name is going to be added to the authoritative server to make sure that the network is reachable, whether it's type A or MX or etc. Now, there could be a security phase to this or a security point of view that can happen with this. But so far, it's been really kept really well and secure. So DNS security is critical because without the DNS, it's going to be really impossible to reach the host by names. We can reach them by IPs, but you can assume or you can think of how hard that would be. So we can have DDoS attacks, denial of service attacks, where the attackers could try to flood the root servers with traffic. And these are the root servers that we said in an infrastructure, they're spread it out globally. And so far, there has been no any type of attacks for that, thanks to traffic filtering. Also, the local DNS often, the local DNS servers often cache TLD servers IPs, which helps bypass root servers. So attackers on TLD servers are more dangerous since they are closer to the user lookup. So that is where the denial of service attack could happen for the DNS with the TLD. We can also have redirect attacks like man in the middle or DNS poisoning. And man in the middle is the idea of intercepting usually. Here it's going to be intercepting DNS queries. It could be man in the middle of packets, packet sniffing, but here we have it related to DNS. DNS poisoning, it's like it sends bogus replies to the DNS server, which it gets cached. It gets cached with false information, obviously. And exploiting DNS for denial of service attacks, attackers would send queries with a spoofed source address like the victim IP, and the target would receive amplify traffic that is overwhelming it. So obviously there came to a defense system or known as the DNSSEC RFC 4033. And that provides authentication to the DNS to make sure, hey, it's really coming from authorized user. And this is also being covered in Chapter 8 when we talk about security of networks. So it plays a key role to make sure that everything, integrity and reliability is up to date with a DNS. So DNS must be protected since as a takeaway, DNS must be protected. It's the internet functionality, and denial of server source protections like firewalls or authentication like that specific DNSSEC are critical defenses that we have. And firewalls are not just to protect DNS, they can also protect harmful traffic and filter that out. So here, so far, we are done with part of the lecture regarding DNS. We will work a little bit hands-on to try some of the record types and the different commands that we do have. And then we will get back into, we'll talk about video streaming when it comes to networking. So let me here and okay, so the first thing we're gonna do is I have it here. We're gonna open also mobile xterm because some of the commands that we will do, you can apply them in the command line like nslookup. But when we use dig, which gives us more detailed, and it's an add-on on nslookup, we will need to use mobile xterm or the Eustace server. So you should already have mobile xterm installed. If you don't, you can use you can telnet using your command line on Mac, but on Windows we had an installation for it. So the first thing we're gonna do is the nslookup command. Okay, and this is gonna be here specifically. Now, with the nslookup that I said, you can do an nslookup with the CMD. So if you're interested, you can open your command prompt and you would just do nslookup. And also, if you go on Google and just search nslookup websites, there's websites that already have all that data available, and they keep it up to date. I think if you just do nslookup websites, yeah, you have nslookup.io and a lot of cool websites that also keep track of that information. But that's beside the point. So if you are planning to do it from the command line, you would just do nslookup. And today we're going to work on the UCF main as a host. So you type in the host ucf.edu. It would reply with various addresses, server, the main server that we have, and the address for that server. So we'll just explain the results in a minute. So that is just one way of doing nslookup. Let's go back and do the same process with mobile xterm. And we do read SSH, which is port 23. And this is going to be Eustace3.eecs.ucf.edu. I believe that should be right. Okay, that's good. Okay, so here we are, and the first thing that we're going to do is we're going to do nslookup, and you should receive the same result on the command prompt. So nslookup ucf.edu. And now nslookup and dig itself, they kind of, oh, sorry, it's not shared. Give me 1 minute. Yes, so this is the first command that we're gonna try. We're here on command line and we did the NS lookup. We're just gonna redo it with sure. And we're just gonna do it with mobile extern. So NS lookup is just quick and simple. Dig is detailed queries and it supports record types, the record types that we mainly discussed in the lecture. So if we do NS lookup, it would give us the same result as we compare it to the CMD. Here is just more, a little bit more in detail than the command prompt, but the IP addresses should be the same. The server here is being changed. It's not .53. But here we have some private IPs and we have public IPs. So here when I was working on it at home, the server is the local resolver on Eustace. This is the system DNS, the server that is related to the Eustace. That's why we see a difference when it comes to the command prompt and the mobile extern. The non-authoritative answers is this is the resolvers that is given to the reply. It's not the authoritative DNS servers. It's just server IPs that are available on the given DNS server of UCF, and some of them are private and public. So it shows, NS lookup shows like which DNS servers were axed and the final IP addresses for ucf.edu. What we can do as well is we can use dig, and dig is going to be a little bit more in detailed. This is going to output the same query intel, characteristic intel of a DNS query that we talked about. Question, answer, authority, and additional that we talked about in here. Okay, so this is more of a detailed way that we can do. And it's going to be, instead of NS lookup, we're just going to do dig. And you can see for yourself, dig is not going to be available on, it's not supported, or it's not found on the command prompt. So we do dig ucf.edu, and this would give us various things. The first thing that we need to look at exactly is that this status here, NOERROR, that we have here. And this is basically saying it's similar to a status code of 204 that is saying, hey, the request is successful. And here we have a lot of IP addresses as well, and they're going to be similar to the ones up here. But this is more in detail. So we have the query time, which took 0 milliseconds, which was very quick. We have the server, which is the same server that we have up here with NS lookup. And we have the message size as well. So you can think of as NS lookup is just a more detailed way to find more information that you're asking for. Then we want to ask for different records of the DNS that we discussed about. So then when we would still use dig because it gives us a more detailed response, but we will request the MX, which is we want to find out, hey, what are the mail exchange records for this specific domain? So we use dig MX and then we provide the host name. Okay, so let's try it here. Dig MX. And I think we can try it lowercase, but I don't think it will work. You have to specify. No, it works as well. So it doesn't really have to be I type in MS, should be MX, dig MX, ucf.edu. Okay, and it should give us the same intel as the figure. So it would give us the mail servers, the SMTP servers for UCF. Here, this 3,600 is the time to live. This is that says, hey, the record is valid for 1 hour before you refresh, that we talked about. Here are the mail servers that we have, UCF smtp.mail.ucf.edu and their associated IP addresses. We also have the server, the main server, DNS server, that it's going to be the same that we've seen in the other requests. The time of the query as well, and also the successful message saying that it is granted is also being showed here. So that is to find out the SMTP or the mail servers of a specific domain that we have. Also, what we have here is the DIG-NS. That is a different type of record. And this is to give us the name server record. And also shows up the authoritative name servers. So we do the same thing. It would be here just DIG-NS ucf.edu. And this should give us the authoritative name servers. As we can see here, it's very close and related to the image. You might notice here it does not give you any authoritative servers. That does not mean that the command is not working properly or it's not giving you the exact details. The answer is the answer for the authoritative servers, since this type of record you are requesting is asking for the authoritative servers. So the answer would be here is the authoritative servers for UCF, their host and their time to live. Also gives you the additional section that we talked about, gives you the different IP addresses for these different hosts that we have. And the main server that we have is going to be the same as for different requests and the time. Also, as we might notice here, the status is also the same, and we are querying, and this would be the response. Here, it took a little bit, 3 milliseconds, so just keep in mind of that. So this is that I wanted to show related to the DNS on how we can find these specific requests for a host. And as I said, you can use the website. You don't have to do all of that, but this is a cool way to give you the hand-on and the practical way. So we can go ahead and close mobile extern because we will not use it for the remainder of the slides. And give me 1 second. I'll stop sharing here and I'll share the slides. So where are we here? Okay. So we have 2 more mini, I would say, modules to cover, part of the application layer. And one of it is really cool. It's the video streaming and content distribution networks. And this is something that's related to all of us. We all like to watch TV. We all like to watch videos on different platforms like Netflix, YouTube. And we're going to see how that works when it comes to the aspect of networking or the application layer itself. Because you realize on Netflix sometimes when you start watching, there's a little bit of jitter. It's not clear, and it takes about 5 seconds, 4 seconds for it to clear up. On YouTube, you have the option where, hey, you can specify which quality you want to see the video at, but this is on your own sake. That meaning if you put a higher quality, the video might stop and there might be jitter in it. But if you lower the quality, then it will go smoothly. So this is what we're going to be discussing about. We're going to be discussing like video streaming and CDNs that we're going to talk about, distributed infrastructure, how companies like Netflix or YouTube would distribute their servers and store and localize what they are presenting. Because as you know, there's creators that we watch on YouTube and videos are getting published every day. Movies are being published every day to Netflix. So how do they keep track of that? And this is where we're going to look at. So as you might know, streaming is one of the largest consumers of internet bandwidth, if you didn't know, and it takes up 80% of residential ISP traffic. This could be Netflix, YouTube, Amazon Prime, any of those. But the idea with that is there becomes a challenge, and the challenge is that we have is how do we scale, and the other challenge is how do we be heterogeneity is like how do we have different variations of users that we have to deal with. So when we come and talk about scaling is how do we reach 100 of millions or even a billion of users? Because let's say we have a movie that is coming out and we have 100 users who are interested in it. Like, give me a movie name. It could be Moana, and everyone is interested in watching Moana. So how does that reach a million of or a billion of users? We want to distribute that in an efficient way. So having a single mega server that would handle everything is not the right option because this server can have fault, and when it becomes into fault, then it becomes down. And there can be a lot of overload on it. Also, coverage is not ideal. So when we scale, we require to distribute the content across many servers worldwide. The other challenge is how do we the variation is not all users have the same type of connections. We have different ISPs. You might have AT&T, I have Spectrum, you have something else, and the type of service that you have might be higher than me or lower than mine. So how do we deal with that as well? So some users are on fast wired broadband, some on our slow mobile networks. We watch videos on our phone when we're outside. Some have bandwidth-rich environments, others have limited capacity. So the video streaming, we have to make it adaptable for the scalability challenge and for the variation challenge. So the solution is to build a distribution application level infrastructure, specifically called as the CDNS, which is content distribution networks that we will talk about. The idea is that we want to distribute videos. We want to make our users happy, where they have different variation of networks or that such that it's scalable to them, to all users that they can watch and enjoy the content that is being presented. So when we talk about multimedia as the video itself, if you are interested to know more about videos and images, I know when I was studying, there was a specific course for image processing or computer vision that talks about the image in detail because there's a lot that goes to it. But here we will just cover only the relation when it comes to the network side. So a video is just a sequence of images that are called frames and shown at a constant rate of 24 to 30 images or frames you can think of per second. And each frame here is a digital image, which is a grid of pixels, and each pixel is represented by bits. Ideally, when the first picture came out, black and white, it was zeros and ones. The zeros would be, I think if I can recall, it's going to be black, and one, it's going to be white. But color came into it, and then they had to find a new way. So there's a lot more into images. So for us to reduce the size of the video, we have to use coding techniques that take advantage for the redundancy. And we have two ways to do that. We have spatial and temporal coding. So the spatial it looks within a single image. And so instead of storing like repeated purple sky pixels, it just stores the color once and the number of times it repeats. For the temporal coding, it's the frame that is I that we have and +1, meaning that it is very similar to frame I. It only sends the differences between them instead of a full new frame. So these are the different coding techniques that we have. And the video coding can be grouped into two broad classes. We have CBR, which is constant bit per rate, and VPR is variable bit per rate. And we said with CBR, which is frame I, the encoding rate is fixed. The video is always recorded and transmitted at the same time, regardless of the content complexity. VBR is kind of a little bit more dynamic. The rate changes depending on how much spatial and temporal coding can be applied. To give you an example, is a scene with a little motion may require fewer bits, while a complex or fast might require fast bits. So it is adjustable. Examples of moving pictures that we have: common video encoding standards, MPEG1, and we have 2, and we have also 4. 1 is used in CDM or ROMs, RLMs, and it is about 1.5 megabits per second. MPEG2 is found in DVDs and accounts for 3 to 6 megabits per second. MPEG4 is mostly used for internet streaming, HTTP streaming, and that varies from 64 kilobits per second up to 12 megabits per second, depending on the quality and the bandwidth. So the choice involves a trade-off. The trade-off is that CBR is static, VPR is more dynamic and more efficient based on what we have. So let's look at a simple scenario that we have here. Streaming stored video from a server to a client over the internet, right? We said there will be two technical that would arise. We have a video server that has storing the video, and the client that is asking for this specific video. So the first challenge is the bandwidth itself between the server and the client can change over time. It's not consistent or not stable. The variation could be is that because there's caused by congestion at different points, like the home network, it could be the access network or the core network, or even the video server itself. So that could be congested itself. Because of this issue or this challenge with the bandwidth, streaming system must be adaptable so that the bandwidth is fluctuating based on what is going on. Packet loss and delay and a packet switch network. There is no fixed guaranteed delay. Delays between like the source and the destination can also be there. We can have packet loss and delay due to congestion. This is going to be result in a poor quality video that the quality is not right, or you're watching a game and it stops or lags, it gets delayed. So that's why streaming requires mechanisms to adapt to changing bandwidth and the variable delays that we have to ensure smooth playback for the user. And we will see the different techniques that they will apply when it comes to this. So let's look at the different steps when it comes to streaming stored videos. This is basically the server is storing the video. And the first thing it does is in step 1, which is the black curve that we have, is it's being first recorded. Then the second step, which is in red, it is being sent from the server to the network on the red curve. And then finally, the third curve that we have in blue, it's received and play out to the client. On the x-axis that you might see here is that we have time moving forward. On the y-axis, we have the cumulative amount of data, either recorded or transmitted or played out. So that is for the y-axis. So we notice how this works in practice. First, the video is recorded and it's stored at a fixed rate of 30 frames per second. The server then transmits the video, often at the same rate. After some delay, the client can begin the playback before the entire video is received. For example, you can imagine is that with Netflix or YouTube, it doesn't make you download the whole thing for you to watch it. You can start watching while the rest is still being sent. And you start watching the video and it's good for the next 4 seconds. And then when you watch this 4 seconds, it sends you like the next 4. So it is kind of adaptable. But sometimes when you skip a video, sometimes it takes time to load. And another thing is that a user might not need all the video to be stored, because we watch a video, we stop and we leave. So we don't want this is becoming insufficient for us. So the key advantage of streaming is that the client begins playback earlier instead of waiting for a full download. If the viewer stops halfway through a video, then there is no bandwidth that is being wasted because we left the video. This is why platforms, like we said, like YouTube can deliver click and play, which is a smooth instead of making you download gigabytes up front. And sometimes when you start a video and we stop, you see that when you come back or it takes you a minute, the video is fully loaded. So you can skip with and to which part that you have without any delay. So on the client side, there's also continuous playout constraint. Once once the playback starts, the client must keep displaying frames at the right time, just like when they were recorded. If the video doesn't arrive on time, the playback stalls. So the problem with when it comes to networking, we said the networks is variable. So this is known as it could cause jitter. So to smooth this out and to solve this challenge is that the clients use a buffer. So when you play a YouTube video or something on Netflix, it loads a few seconds that we said before starting, then that buffer is to handle the delay variation. If the buffering is not enough that you have for the client, then what would happen is that you would see the spinning wheel or the loading icon. And other challenges that are included in streaming stored videos is that client interactivity. They might pause or they might rewind or fast forward or jump through the video. The system must be able to handle that smoothly. And also another one is packet loss or retransmitted that could be dropped, so which can cause more delay. So streaming requires mechanisms to deal with the delays that we have, the buffering, and the user interactions. So we have to keep track of three factors while maintaining a continuous playout. So let's revisit the streaming diagram, but assume variable network delay. In the earlier diagram that we had, delays were constant, so the steps looked even. Here that we have the red, which is the transmission is smooth, but the black, which is the network delivery, is uneven. Some frames are delayed longer and others arrive sooner. Because of this jitter, the client can't just play the video as soon as the packets arrive. So that's why we use a buffer. The tricky part comes when we have user interactions. Like, how do we decide how long the client should wait before starting the playback? If the buffer is too short, the frames may not arrive in time. Users see freezing or a spinning wheel. If the buffer is too long, then users usually get frustrated, hey, for waiting for the video to be played, and we usually don't like to wait for the video to happen. So Netflix and YouTube, what they do is when you hit play, it loads a few seconds into the buffer. If the network slows down, the video keeps playing from the buffer, but if the delays are too high, you'll see buffering spitter if it overloads the buffer that you have. So client side buffering between wait time and smoothest playout. This is the idea that we have as we go down, we have an issue and we see how we can solve it. So this is the ultimate solution that would solve everything, which is called DASH, Dynamic Adaptive Streaming over HTTP. And this is what currently infrastructures are using and streaming companies are using. Obviously, there are servers included with this as well. And this is the approach that we talked about by YouTube, Netflix, and Hulu. Now, the dash from the server side we have, and obviously the client side. The server side, what they do is they divide the video file into chunks. They wouldn't record it fully. And each chunk is encoded at different bit rates. It could be low, medium, or high. And this is based on the quality that you choose. Then a manifest file, it provides URLs for the different chunks. And basically a manifest file, when it comes maybe to even app development, it contains all the summarized important information in the app. The client measures the current bandwidth condition, requests chunks at one time from the server. This is all being done via networking. If the bandwidth is high, you can choose a higher quality, but sometimes when we choose a higher quality and we see it does not work with us, we go and we degrade down to a lower quality. So when you're watching Netflix, if your Wi-Fi weakens, the video may suddenly shift from HD to SD. Does that happen on Netflix? I know that it happens on YouTube, but on Netflix, does it get switched? Like the quality from HD to SD? and then it comes back when the network picks up? Or do you guys not use Netflix to watch?
Sometimes, but like, the video, and I like minimize it, it'll switch it to like SD-Ben.
Mhm.
It's a smaller player, so it doesn't get it.
Yeah.
Second, when I full screen again, it takes me a second to.
For it to be HD, yeah. Yeah, so once the bandwidth improves, Dash would request higher quality chunks again. So the solution, the Dash is is for adaptive video quality dynamically instead of freezing when bandwidth fluctuates. And we will come into the details, talk about it. So with the Dash, the client has controls. It ultimately makes the decision. We have the manifest file, which has the chunks of video, and the client chooses when to request the chunks. It avoids buffer underflow or overflow at which bit rate. And basically, this is the quality. HD bandwidth allows, lower if not. Where to fetch, and it's going to be from the nearest content distribution network or the best server. And this is basically going to be related to the ISPs and IXPs, the internet service provider and internet exchange points that when we talked about the infrastructures. They would ideally also have servers for content distribution networks. And this is just specifically maintained just for the content. So streaming with encoding plus Dash plus the buffering, it works together for a smoother playback. So now when we speak about content distribution networks, we want to ask, how do we stream a video from a massive catalog, maybe a million of videos to 100,000 of users at once? We have a lot of users, they can request the same video or the same movie. And we said that one solution is to use a mega server that stores everything, but that is not the ideal solution for us, as it's single point of failure. If it fails, then everything goes to wrong. Point of network congestion as well. There can be a congestion because it is one server. Long path to distance client. If you are far away from the server, you'll have a distant geographical location from the main server, and multiple copies of video is sent over ongoing link. And that is could be wasting bandwidth. So the bottom line, a mega server is not the solution. It does not scale. That's why YouTube or Netflix, what they do. Oh, that died on. Okay, as long as this one is good. They need more distribution solutions, which is content distribution and networks. The real solution for large scale video is going to be CDNS that stores multiple copies of the videos across the distributed sites. So a CDN or DNS or manifest directs users to the nearest server with the content. And there is two main models that comes with the CDN. We have Enter Deep, which is pushes CDN server deep into many access networks that is closest to users. An example of that, we have Akami that has about 240K servers deployed in more than 120 countries. And I think that could be outdated as they have advanced. Also, the other model is the Bring Home, which uses fewer, larger clusters that is near the access network. That is Limelight that we have here. So the idea of CDNS, the content distribution networks, tries to bring the content closer to the users, such that it reduces the delay and improves the quality. Here is an idea that we have with Netflix. So Netflix has its own CDN, content distribution networks servers, and they also use Amazon Cloud. So what it does is that it prepares the video in 3 steps. First thing that it does is ingest, uploads studio masters, and you can see that the Amazon Cloud will send different versions of maybe the video to different CDN servers. The process transcode into multiple formats or bit rates, and then distribute. They upload it to the CDN servers, which is the final steps. So during the playback, which is like when the user is playing the video, what would happen is that it picks the best CDN server based on geographical location, and the client fetches around the 4-second chunk via HTTP. This is the first second that gets stored on the buffer for it to play. And there's also a dash ABR algorithm that is kind of a little bit of our scope and how it adjusts quality automatically. That is the adjustment that we said about if the video of the bandwidth is not very strong, it adjusts it to a lower handleable bandwidth. So the quality becomes will have a decay. So here's a case study with YouTube. On YouTube, what they do is that YouTube runs on Google private CDNs with clusters worldwide. Netflix and YouTube have clusters worldwide. This is the idea that we distinguished using a mega server. So the videos are uploaded into multiple versions as flash bit rates, and then it's also delivered to the nearest CDN server. And here with YouTube, there is no dash. We are not using the algorithm here. The user is the one who is responsible of the resolution that they want to watch at. Sometimes you see it automatically gets adjusted. Sometimes you start a video and it's at 480 or 720, then you have to change it. Netflix uses the adaptive streaming, which adjusts the quality automatically. So with Netflix, you don't have an option. It would just pick up and decrease by itself. So, but they both rely on private content distribution networks to deliver videos at a scale. Here, we're going to have an example on the next slide. This is basically the same infrastructure that we had. We had different, we have different ISPs, we have regional points, we have internet exchange points, and we have Netflix in this idea. We want to see how this works. So we have Netflix, which has its own servers that we set, and also uses Amazon servers as well. So what would happen is that users open Netflix and request a video, right? This is going to be the user, you. So they're going to request the movie Mad Men. And we said that the content gets sent to almost every server in chunks. And the manifest file is sent to the user depending on which chunk of the video that they want to watch. Then what would happen is that the client says, I want Mad Men, and it would request it from the CDN from Netflix itself, saying, hey, where's this movie? Then it would give it the manifest file, and then it's going to redirect it to the nearest CDN server. Sometimes what would happen is that if that server is congested, what would happen is that it can choose a different path to a different server. So when it comes to the networking infrastructure, Netflix itself is not an internet service provider. It's a point of delivering content over the ISP's networks at the application layer. That is why it's called over the top, right? So they're called over the top because they ride on top of the existing IP infrastructure. And there could be also challenges is that which CDN node should serve the content, how do we handle the congestion and user behavior during slowdowns, deciding what content to store, and at which CDN node. So here, these are some challenges, but the bigger picture is that the internet is the platform, while the OTT is services like Netflix that build on top of the application layer. Here, I just want to do a quick comparison that we have with the different strategies of strategy 1, which is enter deep, and strategy 2 is the bring home. And the different approaches that we have. We said a single data server is one massive server that will store all the videos. And we said that there could have a lot of challenges, such as many ISPs hop, or even it's not or continental. Any weak link that could happen could cause buffering or freezing. There is a single point of failure, and the popular content is sent over the same paths. To make it efficient, we said that we use the CDNs, where we put multiple servers and we distribute them worldwide. That caches content near users and routes requests to the best performing server. So the disadvantage of that is it is going to be more complex to manage, It requires replication, eviction strategy for the content. We talked about the strategies about deep and bring home. The strategy one, enter deep, is that we put many clusters inside access ISPs like the Akami model. And this is basically closer to you to the users, where lower delays, better throughput, but it's harder to manage at many distributed sites. Strategy two, which is the bring home, we have fewer larger clusters at the internet exchange points, at the IXPs, not near the internet service providers. That becomes easier to maintain, rather than having servers closer to the ISPs, which becomes harder to manage. So slightly higher delay compared to the deep approach. So these are the two that we have. And sometimes infrastructures like Netflix or YouTube can use both, or Google. Lastly, that we want to talk about, maybe just to give you an idea of it, but the socket programming with UDP and TCP. I'm just going to go over the main idea now, but hopefully I can go a little bit more detail on it on the next lecture. So this is the programming assignment that we do have. And the goal for us to do that is, we said an application has many processes, and these processes are basically the tasks that the application handles. So maybe that's a website you can watch videos on, and you can also upload videos on. That becomes a process within the application. To know which process we are dealing with, we assign a port number to it. And this is a unique number that we have. And we've seen what port numbers are. They're unique. Like for HTTP, it's port 80. For HTTPS, I think it's 443. For emailing that we use is 25. For SSH is 23. So we have different port numbers for the different processes. So the socket is the interface that would deal with the client and the server as well. So it's basically, you can think of as a door between the application process and end transport. So the process would be ideally in like the application layer, part of the application layer process. It's controlled, and that is controlled by the app developer. But when it comes to the networking, it's controlled by the OS. So that is to give you an idea of the programming assignment, but you don't need to worry about it now. Your next assignment will be the homework one. And the homework one will be about the HTTP protocol and the DNS, SMTP, and it could be could be a true and false question. So that is it for today's lecture. And once I release the homework, obviously I will send an announcement, and the deadline will be kind of a nice deadline. It's not going to be due like within a week, similar to the Wireshark. So you should have a lot of time to finish it. And also, if you don't have, if you happen to have something, shoot me an email to let me know. And also, we have the late policy after 2 days, so that you would lose 25 or 50 if you submit it by 2 days late. After 40 hours, it's not acceptable. So that is it. If you have any more questions, you can ask me. If not, then class is dismissed. So Miguel, if you watched the last lecture, I spoke about the Wireshark assignment when it came to question 2. So the thing is that once, depending on your browser that you're using, if you click on the direct link, what usually happens is that the browser would change it from HTTP to HTTPS. And so that is the idea of modern traffic and what they do. The idea that we provide a PCAP file is that it should already show the traffic. What you're saying here, it shows traffic to a NASA site where I asked in the assignment. That shouldn't be the case, because, yeah, you as well. The file that we traced is a file that is related to the website. So I'm not sure. You have to maybe you can stop by office hours or the TA's office hours maybe filter, did you try filtering based on the IP address of the host? And looking for HTTP traffic. Also, for the students that are here, what you can do is you don't have to use the file. What you can do is you open the file on the browser and then you would just remove the S and then refresh the website. That would also give you a solution. Okay, so that is one idea for you. Okay, this sounds good, Miguel. We will definitely discuss about it. You guys have a good weekend and take care of yourselves.